Okay. So the goal of the talk is to discuss a very simple case of SYZ mirror symmetry for toric Calabi-Yaus. The general case is something we're still working on, but this case already reveals some interesting structure, and I think it's interesting. So the case that I want to consider are the unfoldings of the universal unfoldings of the AN singularity. So in general, this is some singularity which is UV is the product of ZI for I goes from 1 to n plus 1. So you have this singularity, which is the universal unfolding, and so you can resolve this as a toric singularity, and you can resolve it, find a Kreppin resolution. But so the example that I want to, if there's an example of things that people care about, if you considered the A1 singularity, then this would be UV is equal to Z1, Z2, and the resolution is this local P1, which is the total space of O of minus 1 plus O of minus 1 over P1. So the question is, first question is, what is the mirror? And so the way to construct the mirror, so we're going to consider another space. So actually the mirror construction, the way I'm going to describe it is kind of a cheat. I'm going to start with the mirror and use SYZ to recover this space Y, but you could also go the other way as well. So I'm going to start with the space X, which is sort of a fiber product of conic bundles, and it's a fiber product of conic bundles. Why? Because what does it look like? Well, so in the base you have if you consider the W plane, then generically this map looks like a product of C star to the C star to the I. So the fiber generically, but over these special points minus AI, then some of the fibers, they collapse and the fibers become singular. So you have this singular torus fibration, or you have this singular conic fibration, and then the first step is to build an SYZ fibration on the space X. So what you can do is, well, you notice that there's a T to the I action, where E to the I theta acts on X, E to the I theta J acts on Xj, Yj, by sending it to E to the I theta Xj, E to the minus I theta Yj. And so you can consider the moment maps for this. So you get a map to Ri times R by considering the moment maps for this fibration. So you have the different mu i's, and then you also consider just the log on the norm of W. And so you have this Lagrangian fibration. And if you think about what it looks like, so generically, so if this is so we can project to the last coordinate. And so if this is the last coordinate, you have a bunch of, log of norm of AI. And so what happens is that generically your fibers don't bound any, you don't bound any holomorphic disks, so you get a bunch of charts, C star to the n, or C star to the I. And however, exactly when your torus lies over this, has this projection to this last coordinate, you have if that your torus, so one of the factors will look like this, and it will bound a holomorphic disk, which you can kind of see visually. So over these factors, it bounds a holomorphic disk. So you have a bunch of chambers, and the point is that you get a bunch of charts that you have to glue to the general SYZ philosophy says that you have to glue these charts together to get the SYZ mirror. And the formula for doing this was done in a recent paper by Abu Zaid Aru Katsarkov. So the theorem, which is basically due to Abu Zaid Aru Katsarkov, is that the SYZ mirror is, when you glue these charts together, you get exactly this thing that I started with, so this y, but minus these divisors, the union of these divisors, zi is equal to 1. So this is the mirror to this this x, and the question is what is the mirror to y? Well, the general SYZ philosophy says that the mirror, compactifying by divisor should be mirrored to equipping x with a superpotential. So the question is, what is that superpotential? So the lemma is that the superpotential, so y is SYZ mirror to x equipped with the superpotential, which is the sum of the xi's. And so now you can take these statements. This is SYZ mirror symmetry, and you can take these statements and try to say something about homological mirror symmetry. And so this gives you a bunch of potential homological mirror symmetry statements. So the one that I'd like to focus on is, so it turns out that the direction of homological mirror symmetry, which would say that the matrix factorization category here is equivalent to the derived category of coherent sheaves here, is trivial because this space y has no symplectic topology, and this space x, the corresponding function, has no critical point. So both of these, from the point of view of homological mirror symmetry, that both of these things are don't contain any interesting information in that particular direction. But what is kind of an interesting, what you can analyze is you can consider matrix factorization. You can consider the derived category of coherent sheaves on this and the derived category of coherent sheaves on that, and try to compare them with some sort of Fukaya category on X. So the one that I'll look at is the following. So we can ask the following question. So the question is this equivalent to, in this case, what you want to use is the wrapped Fukai category on X? And the answer is, I don't know, but I can prove the following theorem. And this is joint work with Ueda and Chan. The theorem is that there's a fully faithful functor so there exists a fully faithful functor into here. And the problem of showing it's an equivalence is, you have to show that it's essentially surjective, and that's kind of a, there are tools to do that, but I don't know how to apply them to this particular problem. So how much time do I have left, or am I 5 minutes, something, 10 minutes? 15 minutes? Okay, great. Okay, so I wanted to say a few words about why you might expect a fully faithful functor like this. So to begin with, you should think about what the wrapped Fukai category of something even simpler, which is C star, which we view it as a, we want to view C star as the cylinder well, I know to draw it this way. As the cylinder T star S1, and then I want to consider this cotangent fiber, and I want the wrapped Floer homology. What it, it's the thing that's adapted to non-compact domains. So it says, consider a Hamiltonian, which is, looks like the norm squared in the cotangent fiber direction, and then and then use that to translate, to push this Lagrangian off of itself, and and then use that to define your Floer homology. So what happens is it ends up, intersecting itself. There ends up being an infinite number of self-intersections, in both directions. So what I want to do, what I want to do is I want to notice that, so I have this Hamiltonian in the base, and I also have some, my fibers are also C star squared. So I can consider on X, I can consider a Hamiltonian of the form so there's the two there's the fiber directions, and there's the base direction. And so what happens are I get now I can consider a Lagrangian, which is basically fibered over, which is fibered over this cotangent fiber, and also looks like a cotangent fiber in the fibers as well. So you can make it be actually a cotangent fiber, and then parallel transport it along that Lagrangian. So I have some Lagrangians L, so I'll call this Lagrangian L bar, which lives in the base, and then I have some actual Lagrangians in X, which fiber over that Lagrangian L bar. And I want to use this Hamiltonian. Using this Hamiltonian, I want to compute its wrapped Floer homology. And you can do this in such a way that L is a section of your original SYZ fibration, so you should expect that it corresponds to a line bundle in the mirror. So L is some Lagrangian, right? So it's best to so when I'm computing this Floer cohomology, it's actually easiest to lift, so we can lift L bar to the universal cover. Of C star, and then the wrappings that I've done. So this will be my L bar, and then my phi of L bar. Well, it'll intersect it at a bunch of. So let's say my phi of L bar is actually, let's say it's this one. Phi sub h of L bar. And then I also, to compute the product, I'll need to look at phi of h squared of L bar as well. And then the product is given literally by counting, triangles like, say, this one in this universal cover. So all of these are actually embedded triangles. Now, if you looked at the triangles downstairs, there would be some kind of immersed triangles. But now they're embedded, and so the question is now how the idea, the strategy for computing the Floer homology is to use this projection and try to figure out. So what you notice is that triangles, so triangles contributing to the Floer product of L are sections of these triangles here, which are sections of the fibration. Over triangles so you have this fibration and you have these triangles and the section and then you want to figure out how these triangles lift, what are all the possible lifts of these triangles to the total space of the fibration. And it turns out that there's machinery due to Seidel that helps you answer exactly this kind of question. And this, so what does the machinery say? Well, it says the following, it gives you the following proposition. So, yeah. How do I want to? Well, so I need to fix some notation to say it. So if we have so the intersections in the base we'll label elements intersections between phi h of L and L by Q A I1 I sub J. So if you consider what the self-intersections are with this Hamiltonian, so you have some central circle, and then for each, if you look at this picture, for each distance from the central circle, we'll label things in this direction by I and this direction by minus I. So this will count the distance in both the positive and the negative direction from the central circle, and similarly in the fibers. And the question is, what is the formula? So how can you compute the section? So the proposition a triangle contributing in the base, so a triangle contributing to Floer homology in the base must be weighted by the product of 1 plus Q0 1, and this is in the jth component, to the dj, where dj is the intersection number so you have this triangle delta of delta with aj. So you have this these monomials. So a triangle contributing to this Floer product is going to be weighted by this weight, and when it's where that's the intersection number with that particular piece of the discriminant locus, and so that basically, so ordinarily you have in ordinary Floer homology you have that so for L bar you have that you would ordinarily have that equals to 1, but in this case you instead get the product of 1 plus U0 1 in the jth position to the dj, or in this case it intersects each of them once, so it's just this, yeah. So this particular product that I was describing, it intersects only once, so you get exactly this. And then the map with the original ring sends Q0, this Q01 in the jth piece to Zj minus 1. I'm saying to compare to the original algebra that we were supposed to get at the very beginning. And then this goes to U. And this goes to V. So this exactly is the product, the relation that you were supposed to get from the very beginning. But it comes out. You can see it from the Floer homology, I guess is my point. Is that it? 2 minutes? Oh yeah. Okay. So the last thing that I wanted to say, I guess I don't have more to describe. If you do more of these kind of computations and use this proposition, you can get that fully faithful embedding that I was talking about. But the last thing that I wanted to say is even though we can't, at least I don't know how to prove homological mirror symmetry in its entirety, there are other things you can think about, that other interesting instances of mirror symmetry. So if we consider the mirror that I had X, you can So if you consider X, you know that it's this xi, yi is equal to the product of, ai plus w. Well, you can imagine varying these ai's. So you can imagine varying these ai's, and you get a fibration over this. So we'll call it. You get an entire family over the configuration space of I points. I points in C star. And if you take pi 1 of this space, so if you take pi 1 of this configuration space, you get the pure, this is the pure braid group on I generators, on I letters, or I plus 1 maybe. I, okay. This is the pure braid group, and so that you would expect that if you consider the monodromy about this family, that you would get a a similar pi action of the pure braid group on the derived category of the mirror Y that we started with, and that's something that has been checked using the theory of variation of GIT by Donovan and Siegel. So. Yeah, so that's pretty much all I have to say. Thanks. Yeah?
You get that it was embedding because somehow you know that line bundles generate the...
Right. Yeah. You find the mirrors to line bundles, and you know that those things generate the derived category, so that you use that to get an embedding. Because we know how to compute the endomorphisms for sections of the SYZ fibration, and those correspond to line bundles. But the other, we don't know how to show that those sections generate this wrapped category. But I guess other people are working on stuff like that. So.
Any other questions?